Hello and welcome to the fifth session of the fluid structure interaction course. We are going to study the coupling between a structure and a flow for all fluid velocities, restricting ourselves to the framework of potential flow theory. Before starting, let us put ourselves in a course sequence. We have so far classified all our fluid structure interaction problems by comparing the numbers UR and D. We started by studying the case of UR very small compared to D, for which we can consider the fluid at rest. Then, we considered the opposite case. In this case, the solid could be considered at each instant non-moving in the surrounding flow. A less restrictive case was also studied, for which the solid could be considered at constant velocity. Now, we will place ourselves in a case without approximation, where the solid and the flow have comparable velocities. This is a situation called strong coupling. And in particular, we will consider the case where the inviscid approach is suitable. We will be able to use the theory of potential flows. This approach does not betray too much the physical reality of the problem as long as the detachment is not observed. This is the case for actual flow around slender bodies. To carry out this study, we must first know what is the stationary reference solution around which we will study the dynamics of the system. Let us consider any solid represented here by this vertical bar. The solid is in this equilibrium position for U0 equals 0 at infinity. Then, let us consider a flow at velocity U0. The solid deforms and finds a new equilibrium position in the flow. We consider that there is a stationary state of the problem given by a field psi0 with the fields U0 and P0 in the fluid. These stationary fields depend only on space, not on time. What will interest us in particular is the dynamics around this stationary reference state. The displacement of the solid is then psi and depends on x and time. The velocity and pressure fields in the fluid also depend on space and time. In the following analysis, we will consider state 2 as known. Only state 3 will be described. We will also consider that the reference state of the displacement psi is 0. Let us start by discussing the scaling of the problem. As always, we have to choose a length and a characteristic time. In this generic development, let us call eta this length and tau this time. The velocities are then scaled by eta on tau, and the reference pressure is constructed from the velocity eta over tau. All lengths, time, velocities, and dimensionless pressure are introduced. In this framework, the displacement number is psi0 on eta, and the reduced velocity U0 tau on eta. Finally, let us not forget that if we have to couple the fluid with a structure mode, we may also introduce a mass ratio. The dimensionless steady state is therefore described by a solid at equilibrium, having zero displacement in this reference state, placed in an infinite flow at velocity UR. The velocity field U0 and the pressure field P0, both stationary, depend only on x. Since we consider an inviscid flow, the velocity U0 derives from the potential psi0 such that U0 equals gradient psi0. We are interested in the dynamics of the system around the stationary reference state. The perturbations are considered to be small amplitude. The small parameter is noted epsilon, but here again, note that epsilon is equal to the displacement number d. The displacement field is given by epsilon psi prime, and it depends on space and time. The velocity, pressure, and potential each have a stationary contribution of order 0 and a time-dependent perturbation of order 1. And we also have u prime equals gradient of psi prime. We can write our schematic view of the fluid structure interaction problem as follows. Note that the equations in the fluid are the Euler equations. We neglect the viscous effects and the hydrostatic effects in this development. We will first study the problem of fluid mechanics. In this very general framework, we will concentrate on obtaining an expression for the pressure field resulting from the motion of the solid. It is in simpler particular cases that we will carry out the analysis to its end by calculating the modal forces. The specificity of this problem compared to the case of the fluid at rest lies precisely in the kinematic boundary condition. Indeed, without flow, the linearized kinematic condition was written in the same way with only some primes, because both the velocity of the fluid and the displacement of the solid consisted only of terms of order 1. Here, the velocity also has a component of order 0. This complicates the linearization of this equation a bit. Let us develop each term of the kinematic condition. The velocity at order 0 in x is the velocity at order 0 in x naught plus the displacement times the gradient of u naught in x naught. Developing the velocity fluctuation at x gives the fluctuation at x naught and higher order terms. Finally, we need to develop the normal to the interface. Without demonstration, we can reuse results from continuum mechanics, which show that during a transformation given by the displacement field epsilon psi prime, the normal goes from n naught to n, and at order 1, a new term expressed in x naught appears. This term involves the surface gradient of psi prime. It only remains to introduce all these developments in the kinematic condition and to retain only the terms of order 0 and 1. At order 0, we obtain the standard boundary condition of fluid mechanics with zero velocity at the wall, which is logical, since order 0 describes the stationary state for the fluid and the solid. At order 1, we obtain several new terms that involve the stationary velocity field u naught, which was not present in the case of the fluid at rest. Now that the kinematic condition has been linearized, we have to do the same work for the Euler equation. Let us write them first at order 0. We can replace u naught by gradient psi naught in the first line. We then show that psi naught satisfies the Laplace equation. By introducing psi naught in the second line, we can easily obtain this relationship between the potential and the pressure. There is a gradient in both terms, so we integrate once to get that 1/2 of u naught square plus p naught is equal to a constant. This well-known equation is the Bernoulli equation. Here are the two important equations of the stationary problem. The first one governs the potential, the second one links the pressure to the gradient of the potential, that is the velocity. Let us go to order 1. Here is what we get. The only neglected term is the term gradient of u prime times u prime, which is of order 2. By introducing the potential psi prime into the divergence of u prime, we get the Laplace equation for the potential at order 1. The conservation of momentum terms can be rearranged to put this equation in the form of a sum of three gradients. After integration, we obtain an equation which links the pressure to the velocity potential. It should be noted here that the integration constant has not been kept, since it only corresponds to the stationary field and concerns the order 0 of the equations. We have just obtained the unsteady Bernoulli equation, which allows us to obtain the pressure field from the velocity potential. Let us report all what we have obtained. Here is the problem at order 1 for the fluid. The boundary condition is given by the displacement field psi prime at the interface. We will consider in this analysis that it is a displacement according to a mode phi. Later, we will replace psi prime by 2 prime phi. To solve this linear problem, we will represent the solution psi prime as the sum of two fields. One is written ur psi 1, the other psi 2. Each one obeys the Laplace problem with the boundary condition split in two. The first field does satisfy this boundary condition in which the velocity u naught has been divided by ur. U0 on UR gives a fictitious velocity field U bar which corresponds to a unitary velocity field at infinity. For the second field, psi2, the remaining boundary condition is used. In these expressions at the interface appears the displacement or its derivative with respect to time. It is here that we will consider displacement according to a mode. Xi prime equals q prime phi. Q prime phi appears in each term of this boundary condition, and given its form, we can look for a separated variable solution of the form q prime phi psi 1. Phi psi 1 is the corresponding mode for the potential. It is a function of space only. In the boundary condition 2 appears q prime dot. So we are looking for a solution with separated variable of the form q prime dot times the mode, noted phi psi 2. Let us now assume that we have solved the two problems corresponding to the fields psi 1 and psi 2. Recall that since we have normalized the boundary condition for the field psi 1, these fields psi 1 and psi 2 do not depend on UR. This dependence now appears through the multiplicative coefficient in the expression of psi prime. We still have to calculate the pressure. We use the unsteady Bernoulli equation for this. By replacing U0 by the reduced velocity times U bar, we obtain here again an expression where the dependencies in UR appear explicitly. We have thus obtained the pressure as a sum of three terms, the first one proportional to the acceleration, the second one proportional to the velocity, and the third one proportional to the displacement. These terms, once projected on the modal motion, will give rise to added mass, damping, and stiffness. It is remarkable here that we highlight an added damping without viscosity and without transmission of energy to a wave field, as it was the case in vibroacoustics. The solid can give energy to the permanent flow during the oscillation, even without viscosity. Note also that the velocity term, which will give rise to added damping, is proportional to UR, while the displacement term, which will give rise to added stiffness, is proportional to the square of the reduced velocity. The acceleration term does not depend on the reduced velocity. This analysis made for the potential flow generalizes very well all that has been obtained previously. Indeed, we have obtained added mass in a fluid at rest, effects of added stiffness always proportional to the square of the velocity, and effects of added damping due to aerodynamics proportional to the velocity. And if UR is small, we find that the added mass dominates. It was the case with the fluid at rest. If UR is very large, it is the added stiffness that dominates. This was the case when we discussed the aeroelastic phenomena. We will not go any further in this general case, for which it would remain to perform the projection of the pressure on the modal motion. We should not forget that the mass ratio would appear in front of each term of added modal forces. And finally, if we consider not one but several modes, coupling by mass, damping, or stiffness would occur. In the second video of this session, we will complete the resolution and highlight new physical phenomena in a particular case that has many applications. It concerns uniform potential flows parallel to a slender structure.